Hey everybody, welcome back to GR Research, where today we're going to be talking about some misconceptions. The big one that I see often when we do an upgrade kit and we put it out there on YouTube is people will post in the comments section that all I'm doing is making the speaker flat. And they don't want a speaker that's flat because it'll sound flat. And that because the frequency response looks flat, they equate that to a sonic character of how that speaker is going to sound. And they don't want it to be flat because the original designer didn't intend for it to be that way, and I'm just making it different and I'm not making it better. So all those are complete misconceptions. We're going to talk about frequency response versus how does that relate to how the speaker sounds. So first thing to do is keep in mind is when we're taking frequency response measurements, we're using that as a tool, whether it's from my end on the design aspect or if we're looking at something someone's brought in. What we're doing is we're looking at the speaker's accuracy. We're not looking at how the speaker sounds. Granted, if the tweeter's jacked up 3 dB louder than the woofer, that tells you a lot about how the speaker's going to sound. It's going to sound brighter in that area because it's twice as loud in that area as it's supposed to be. Same thing, we see a big hump at 1 kHz. That is a response problem. It's not a sonic character that the designer intended for the speaker to have. So it's going to tell you something about how it sounds by the fact that it's too loud in that area. But that's all that it tells you. It tells you how loud it is over a given frequency span. That's what a measured frequency response is telling you. It is how loud it is over a given frequency range and a given time. So it's measuring when that wave arrives at the microphone and how loud it is and at what frequency. That's it. It's not a measurement of how it sounds. It's a measurement of an accuracy in one aspect, and that's the on-axis frequency response. So we can design a speaker, and I've designed speakers that can measure flat but sound completely different depending on the typology of the parts and the quality of the parts that we put on them. And several times we've done demonstrations of this where we have a speaker and we have two different crossovers. Those crossovers measure exactly the same, but sonically they sound extremely different. We did that with a little Behringer Truth model years ago where we took a speaker from the factory that measured pretty well but sounded dreadful, and we went in and replicated the exact same crossover and put that in there and put switches on the back where you could switch from one crossover to the other, and you could hear a considerable difference between the two even though they measured exactly the same. So take for instance again the speakers that are back here in our listening room, Big and Extremes. It's a huge open baffle speaker and it has a very accurate frequency response, meaning it measures very flat. Does that mean it sounds flat? Absolutely not. It is one of these speakers out there that is the furthest from having a flat sound than any speaker out there. It's full open baffle, it's transparent, it's three-dimensional in how it sounds. There is depth and width to the sound stage. There is dynamics out the wazoo. There's detail levels. All of those things are affected by a whole bunch of other things. The measured frequency response is just measuring amplitude over a frequency range and a given time. And when I say a given time, it's the arrival of that to the microphone. And we look at the time factor when we post measurements of a spectral decay. So a spectral decay shows the frequency response across the top. That's how loud it was over a frequency range, and then how fast it dissipates that energy. So we're looking at it over time. Those are tools that we use to show different aspects of the speaker's performance. If the speaker measures flat, but it has a bunch of stored energy in one area, you're going to hear that stored energy as excessive ringing. If the speaker, of course, like I said, has a jacked up top end or bass that's jacked up, obviously you're going to hear those things, but those aren't denoting quality. And as a reference, we want the frequency response to be a flat line. When the artist originally creates their music, they mix it and they master it and they bring all the different elements up to a certain level that they want. This is the way they've recorded it, and this is the way they want you to hear what they've created. So as a loudspeaker designer, it's our job to create a speaker that's accurate so that you hear the original recording the way it was intended to be played back at the same level. If the original artist wanted the treble jacked up, if they wanted the bass jacked up, they would have done that in the mix. There is no special EQ that is built into a speaker that is just the right settings of amplitude and EQ to make everything sound better. That's just a complete misnomer. It doesn't work that way. We're looking for a speaker that has an accurate response so you hear it the way it was originally recorded, not jacked up. And there's a lot of ways it can get jacked up. And sometimes even the on-axis frequency response doesn't tell the whole story. A speaker may have it may have a little bit of a brightness in the off-axis response, going horizontally off-axis. Or it may have a dipped area vertically in the vertical off-axis response. So a designer may make it a little softer in one area to compensate for those things. Or some of the British designers would design in what's called a BBC dip, which is a softened area that's right in a frequency range where you would typically get a sidewall reflection in a small room. And they're compensating for that a little bit because they want to maintain a level frequency response at the seating position where you're listening. So even though the on-axis may be softened in a little spot or two, that doesn't mean that it's necessarily going to sound soft in that area. You have to look at the vertical and horizontal off-axis responses as well. That's something we look critically at so that we try to create an even in-room response. But still, the on-axis response is one slice of that window there, one slice of the pie there that shows you through that window what you may expect to hear. It's a measurement of accuracy. It's not a measurement of quality, and it isn't a measurement of how good the speaker sounds. The speaker can sound dull and lifeless as can be and be flat and sound flat, or it can measure flat and be the most dynamic, greatest sounding speaker you've ever heard. Those elements are completely separate from each other. So I hope that cleared up a little confusion. There seems to be a lot of confusion out there that just because it's flat doesn't mean it sounds better. It's flatter means it's more accurate. And it does tell you a little bit about how it sounds, but it's not the whole thing. When we do an upgrade, all those other parts that go into the upgrade, the quality of those parts, all have a massive amount to do with how the speaker sounds. And we know because we do it all the time. And we know what effects those parts are going to have. We take an inductor on a woofer circuit, and it was originally an iron core inductor, and we replace it with an air core inductor. We know exactly what that audible effect is going to be. Iron core inductors hold a residual charge. There's a little bit of smearing involved. It blends everything together and smudges it together. It doesn't release the signal as cleanly. An air core doesn't have anything in the center of it. It doesn't store that energy. It releases immediately without the stored energy, and it's cleaner sounding. It's more open. It's more transparent. However, the cost of the air core can be 75% more or 50% more than the cost of an iron core inductor. You see those little iron core inductors in there because it costs a lot less, sometimes significantly less. So when we switch those parts out, we know exactly what the audible effect is going to be, and we can guarantee that we're making an improvement, even though it's not going to show anything different in the frequency response. When we put a high-quality capacitor in the tweeter circuit, we know that there's going to be an improvement in clarity over an electrolytic cap it may have come with, or just an inexpensive poly cap that it had. We already know what that improvement is going to be because we've done it a ton of times and we've listened thousands of times, and we know exactly what's going to happen. We don't have to listen every time to know what's going to happen. It's like pouring sugar in your tea. It's going to make the tea sweeter. We know it's going to make the tea taste sweeter. We've done it already. We don't have to taste it every time to make sure that sugar made the tea sweeter. Same thing with all these parts that we use. We know exactly what the audible effect is going to be. So when we put an upgrade together, we know exactly what we're giving you, and there's a level of improvement that we can stand behind and know there's going to be a level of improvement there. The frequency response is just one aspect of what we may have improved. We may have fixed problems and anomalies, and that's making it more accurate, but that's not making it sound necessarily better. It's everything else we're bringing to the table that makes the speaker sound better. Now, I hope that made sense. If you've got questions, I know some of you just can't believe it, whatever, post them in the comments section. We'll take them as they come. That's it for this little clip, and thanks for watching. Please hit the subscribe button if you haven't, and we'll see you in the next video.